Hi again, everyone. Once again, my name is Maddie and I'm from Massachusetts. Today, we have another lesson in our chemistry unit to share with you. We will be discussing the parts of an atom, how they combine to form molecules, and a few more fun things about atoms and molecules. We're excited to be here with you. The first topic in today's lesson will be electrons, where we'll learn what electrons are, some properties of them, and how they were discovered. Then, we will learn about the concept of a nuclear atom, meaning that an atom's mass, composed of protons and neutrons, is at the center of an atom, known as the nucleus. We will then explore atomic structure and how it is represented in each element's box on the periodic table. Next are ions and isotopes, where we will discuss how some atoms of the same element differ. After we've covered these essentials about the atom, we will begin talking about molecules and bonding, but we'll talk more about these in Lesson 4. Today we will focus on what a bond is, how it makes a molecule, and how molecules and bonds are represented with notations. We'll move on to basic trends in the periodic table with a focus on properties of elements on certain areas of the table and families of elements. Last for this lesson, we'll discuss some standard rules for referring to molecules in English. Let's begin. I'll be starting off the lesson today talking about electrons. On the topic of an atom, it's natural to ask the questions, what is an atom made of, and how are atoms of different elements different? Shortly after the discovery of the atom, it was realized that although atoms make up everything in the universe, they are in fact divisible. An atom contains three parts that are often discussed: the electrons, the protons, and the neutrons. We will discuss the protons and neutrons later, but for now, here is a basic definition of an electron. It is a particle that is so small we refer to them as having no mass, and the particle is negatively charged. Historically, J.J. Thomson was the first to discover the electron using a device called a cathode ray tube. In this next portion, I'll explain how Thomson conducted his experience and how it proved that electrons were a thing. However, it's a bit beyond the scope of this module, so do the best you can to understand, but there's no pressure. Next, I'll briefly describe what the cathode ray tube is, and then I'll show you a diagram. On the ends of a tube are metal electrodes, each connected to a source of electricity. These electrodes can be made of any type of metal. When the cathode ray tube is turned on, fast-moving electrons excite the gas in the tube, causing it to light up. Here's a visual of the cathode ray tube I discussed on the previous slide. This process is known as an oxidation-reduction reaction, which is a complex chemical reaction in which electrons are transferred from one atom to another. To understand this concept of what an electron is and its discovery, however, here's what's important. The negative end of the high-voltage generator sends a negative electric charge, or a stream of electrons, through the tube. The tube is made of atoms, as all things are. When the electrons strike atoms in the glass wall, they get excited and have more energy. When the electrons return to their original energy level, they release energy as light, called a photon, causing the glass to glow green. Since the metal cathodes in the cathode ray tube could be made with any type of metal, Thomson hypothesized that all atoms must have electrons. Later, other scientists were able to use Thomson's work to learn about protons, neutrons, and the masses and charges of all of these subatomic particles. That was a lot of new information, but like I said, it's important to know, if nothing else, that an electron is a negatively charged particle with no mass.
Hi guys, I'm Grace from Massachusetts, and I'll be talking about the nuclear atom. All matter contains negatively charged electrons. So atoms, because they are electrically neutral, also need to contain positive charges to balance out the negative charges. Originally, Thomas Dalton proposed that positive charged matter was embedded in a sphere which made up most of the mass of an atom. It is similarly structured like a chocolate chip cookie. The chips are the negatively charged electrons, and the rest of the cookie is the positive matter, which makes up most of the mass of the cookie itself. This notion was proved wrong by Rutherford's gold experiment. He aimed a stream of particles at gold foil and planned to examine how the particles were scattered by the foil. If Dalton's model was correct, and the atom's mass and charge were evenly distributed throughout the atom, the positively charged particles should have passed straight through the gold foil. Instead, the particles reflected off of the gold foil. This development helped Rutherford conclude that the positive charge in the majority of the atom's mass must be concentrated in a very small space within the atom's interior, which means the reflection was caused by a tiny dense area within the atom itself. This area is called the nucleus. It is the central area of the atom composed of protons and neutrons. Protons have a positive charge and neutrons have no charge. In summary, Rutherford's gold experiment proved that the atom consists of a small, massive, positively charged nucleus with the negatively charged electrons being at a great distance from the center. Thank you guys for listening, and please feel free to reach out to us if you have any questions.
Hi everyone, my name is Meg, and we are now going to talk about atomic notation. On this slide, the periodic table is shown on the left. The periodic table is a sort of map to all the elements known to man. The elements are organized by atomic number and other periodic trends. On the next slide, we will talk about what an atomic number is, along with each element symbol and atomic mass. The periodic table gives us almost all the basic information we need to know about each element. In most periodic tables, the element's name will be at the top of the box. But another way to tell what element is being described is the element symbol. The element symbol is the universal abbreviation of the element's name. For example, oxygen's element symbol is O. The atomic number is also another way to tell what element is being described. Each element has its own atomic number. The atomic number will always be above the element symbol. The atomic number is the total number of protons an element has, and will be specific to each element. For example, only oxygen has 8 protons, making its atomic number 8. Finally, the number below the element symbol is the atomic mass. The atomic mass is approximately equal to the mass of the nucleus, which equals the total number of protons and neutrons. We will talk about why the atomic mass is equal to that sum in the next slide. Each part of the atom has a specific charge, mass, and location. However, since each part is so small, scientists have come up with a specific unit for mass of protons, neutrons, and electrons, called AMU. As you can see from the chart, protons have a positive charge of 1, a mass of 1, and they are located in the nucleus. Neutrons have a charge of 0, so they have no charge, a mass of 1, and they are located in the nucleus. Since both protons and neutrons have a mass of 1, that is why the atomic mass is equal to their sum. Finally, electrons have a negative charge of 1, no mass, because they are so small, and they are located in the orbitals of the atom, or their outer rings. This is a lot of information to take in, so feel free to rewind the video and review anything that you were stuck on. Hi everyone, my name is Meg. We are now going to learn about ions and isotopes. After learning about atomic notation, you may be wondering why the atomic mass is not a whole number. That is because the atomic mass is an average of all the different variations of the element. Ions and isotopes are the two types of variations an atom can have. Ion variations affect the number of electrons, and isotope variations affect the atomic mass. The next slides will describe these definitions further. An ion is an atom with a net electron change due to the loss or gain of one or more electrons. This changes the charge of the atom. Atoms naturally have no charge because there are the same number of electrons and protons. However, an atom that gains electrons has a negative charge because the total negative charge of the electron is now greater than the total positive charge of the protons. When there are more electrons than protons, the ion is called an anion. An atom that loses electrons has a positive charge because the total negative charge of the electrons is now less than the total positive charge of the protons. When there are less electrons than protons, the ion is called a cation. Ions occur to make the atom more stable than it already is. An isotope is an atom that has the same number of protons but a different number of neutrons. This changes the atomic mass. The reason the atomic mass is not a whole number is because there are naturally occurring isotopes for every atom. This will change the average mass for the atom, causing the atomic mass to be a decimal. Isotopes are naturally occurring just like how humans naturally vary in weight, but isotopes can also be man-made through radioactive decay. Ions and isotopes are a complex topic that we just briefly covered, so to get a better understanding of isotopes, try out this online lab.
Hello, in this section we'll be discussing the basics of covalent bonding as well as the concept of molecule. It is important to note first that in order to reach a more stable state, atoms can share pairs of electrons, forming what is called covalent bonds. Well, what does this mean? As a rule of thumb, atoms will react to form molecules spontaneously if and only if the resulting state is more stable than the previous one. But what is reacting specifically? A chemical reaction occurs when bonds between atoms are created or broken. Two atoms that exhibit a non-metallic behavior, which we will define later on in the periodic trends section, typically form covalent bonds, a type of chemical bond that involves the sharing of one or more electron pairs between the two atoms involved. This occurs, in fact, as a result of a balance between repulsive and attractive forces between atoms. Covalent bonding allows atoms to feel their outermost energy level, which, as we will see later, is always optimal for all atoms involved. Covalent bonding is one of the three prevalent kinds of bonding, and it is typically found between atoms in gaseous molecules. But what is a molecule specifically? To effectively explain covalent bonding, we need to define the concept of molecules first. They are units that result from the union of two or more atoms through bonding. Many common familiar substances are composed of molecules that are fairly simple in composition. Two very typical examples that you will often find are the water molecule, which is formed by two hydrogen atoms bonded covalently to an oxygen atom, and molecular oxygen, which is two oxygen atoms connected by a double bond, that is, a bond involving two shared pairs of electrons. As you can see in this picture, covalent bonds are usually represented by either two dots that symbolize the two shared electrons, or one line that represents the shared pair. The concept of covalent bonds is important since it serves to explain lots of different chemical phenomena, from theories such as those of molecular geometry to concepts like polarity and reactivity. But no need to worry about those just yet. We will cover all of them soon. However, it is important for us to note right now that the covalent bonding model is not a comprehensive or all-encompassing model in itself, meaning that it coexists with other important models and theories that altogether serve to the purpose of understanding chemical reaction, experimental observations, and processes.
Hi guys, I'm Liv, and I'm back today to talk a little bit about some basic periodic table trends. So let's begin by addressing the families on the periodic table. elements with similar properties are typically grouped under a general name, and each family is denoted by a color. As you can see, I color-coded the names just so you could find them on the table that I attached, but the colors that are shown on the specific table are not like the standard colors for every sample table, so just be aware of that. There are 8 general family groupings. The first is nonmetals or halogens. The second is alkali metals. The third is alkaline earth metals. The fourth is transition metals. The fifth is noble gases. The sixth is rare earth metals, which kind of has 2 subcategories, lanthanide and actinide. And the seventh is metalloids. The eighth is other metals or post-transition metals. So next I'm going to talk a little bit about the periods on the table. So the term period refers to the rows, which are going horizontal left and right, where the element is found on the table. If the period of an element is higher, you'll find it lower on the table. This element has more orbitals or rings, which causes the nucleus to have less control over its valence electrons, or the outer shell. So this is because the greater distance between the nucleus and the valence shell. If you have information on an element's period and family, you can make an estimate about the ionization energy, which is the amount of energy required to remove an electron from the valence shell. You can also make an estimate about the atomic radius, which is the distance between the nucleus and the valence orbital. And you can also probably make an estimate on the element's electron affinity, which is the ability of the atom to gain electrons and how much energy will be released as a result of that. So as you travel down and to the left on the periodic table, the ionization energy decreases, the atomic radius increases, and the electron affinity decreases. So I have some arrows on this table, and you can kind of look at the direction of everything. It's a pretty good note, just like for general rules. It's also important to remember that electronegativity is the ability of an atom to attract electrons from other elements, while electron affinity gives the amount of energy released when the atoms gain an electron. So it's also like the stability of an atom after the transaction. So although those names are similar, they're different. Okay. So like I mentioned earlier, the elements are grouped in families, and these elements have the same number of valence electrons on the outermost shell, and therefore they have similar chemical and physical properties. So we have the alkali metals with 1 valence electron. They have a low density, a relatively low melting point, and their ions have a 1+ charge. And then we have the alkaline earth metals, which have 2 valence electrons. Their ions have a 2+ charge, and they have a higher density and melting point than the alkali metals. After that, we have transition metals, which also have 2 valence electrons and a relatively low ionization energy. So these families that I just mentioned above, they lose their valence electrons to ionize, and this is because the metals have a low electronegativity value. They also share properties of metals that will be explained on the next slide. So after that, we have lanthanides, which are highly reactive. They have a high melting and boiling point, and they're relatively soft, bright, silvery metals. That's similar to the actinides, which are radioactive. They also have a high melting and boiling point. They are soft, malleable, so like they can be physically manipulated, and they're ductile. So after that, we have post-transition metals, which have a high density. They're very conductive. They have a higher melting point than most other metals. And then after that, we have metalloids, which they share properties of both metals and nonmetals. It varies between the elements, just where they are on the periodic table. After that, we have the halogen families, which have 7 valence electrons. They're highly reactive nonmetals, and they have a really high electron affinity because they have a really high number of valence electrons. After that, we have the noble gases. They have 8 valence electrons, but they have a really low electronegativity because their valence shell is already full. It's been complete, so it's stable. So they're non-reactive nonmetals. Then we have the metal, nonmetal, and metalloid groupings. Metals are found on the left side of the periodic table. On the picture that I added below, they're a blue-gray color, and they have a shiny or lustrous appearance. They typically have high thermal and electrical conductivity, and they tend to be solid at room temperature, and they're really pliable, so they can be physically bent out of shape without cracking. The metals have a metallic character, which means they readily lose electrons from their valence shell to become cations, and this is the reason for their low electronegativity values. Then we have nonmetals on the right side, and they are a little bit of a yellow kind of gold color on this chart, and their properties are inverse to those of the metals, or they're opposite, so they're not shiny, they are not good conductors of thermal or electrical energy, and these elements are not ductile, so they're not really able to be stretched into like thin wires or anything like that, which we see with metals. They typically have between 4 and 8 electrons in their valence shell, which means that they have a higher electronegativity value, and they gain electrons to become anions. So these two groups are separated by a line of elements called metalloids, whose properties are like an intermediate between the metals and the nonmetals, and although they appear somewhat metallic, they are more often semiconductors than they are conductors. So similar to the nonmetals, these elements are not malleable and they're not ductile. So that's a quick summary of the basic periodic table trends. I encourage you to go back and look through these slides again. It can be hard to pick up all the information at once, but you guys got this.
Hi, I'm Grace from Massachusetts, and I'll be presenting an introduction to naming compounds. There are two types of compounds we will be naming today: molecular compounds and ionic compounds. Molecular compounds are composed of two nonmetals, and ionic compounds have a metal. Molecular compounds are named with the first element listed first, and then followed by the second element using the stem of the element's name plus the suffix IDE. They also have the prefixes listed on the side here to mark the number of atoms in a compound. Here on the side is a list of the number of atoms compounded with the prefixes on the element's name. 1 atom compounded is mono, 2 is di, 3 is tri, 4 is tetra, and so on. Ionic compounds are named the same way as molecular compounds, with the first element listed first and the second element having the stem of the element's name and then IDE. Ionic compounds also use the prefixes on the side to specify the number of atoms in the compound. But for ionic compounds with transition metals, a Roman numeral also needs to be inserted after the name of the metal to indicate the transition metal's charge. The Roman numeral is determined by what charge is needed to balance out the nonmetal's charge. For example, FeCl, iron 1 chloride, and FeCl2, iron 2 chloride. These examples show the suffix and the IDE for the second element, the stem and the suffix IDE for the second element, and they show how the Roman numeral is based on the nonmetal's charge. Here are examples for molecular compounds. The di prefix is there because there are 2 atoms compounded, for the first example, H2O, and the second element has the prefix mono, the stem of the element, and ends with IDE. So H2O becomes a hydrogen monoxide. For the second example, Cl2O7, dichlorine, it has the prefix di for the 2 atoms compounded, and the second element has the prefix hepta for 7, the stem of the element's name, and the suffix. Thank you for watching and listening, and I hope this video is helpful. Please feel free to reach out to any of us with any questions.
With any questions that may come up, please feel free to reach out to us, and we look forward to seeing you in the next chemistry video.